Okay, we move on to the production constraint optimization. First of all, the basics. Isoquant. Okay, this is the equation. Quantity is a function of two inputs, long-run production, labor and capital quantity. Marginal product of labor is the first-order partial derivative of the total product or isoquant equation with respect to labor quantity. And then similarly, marginal product of capital is the first-order partial derivative with respect to capital. Okay, and then this is the slope of the isoquant, change of y. The y-axis variable is capital, and over change of x, the x-axis variable is labor quantity, okay, which is equal to minus marginal product of labor over marginal product of capital. And then the isocost line. For the isocost line, cost is equal to the labor quantity times the payment for each labor, which is wage, plus capital times rent. R stands for rent, actually. Okay, and then the slope of the isocost line is minus W over R. Okay, and then at equilibrium, when isoquant is tangent to isocost line, then you have this relationship. And again, we would take out the negative sign, okay, on both sides. Okay, and this is the graphical illustration. Okay, and then for the production type questions, there could be two types of questions being asked. Okay, to calculate the labor and capital quantity that will minimize cost. Okay, to produce a particular level of output. Okay, in other words, Q is given, but you must find out labor and capital quantities, and then this minimum cost. The other type of questions would be the other way around. You are rather given the cost constraint that you are only allowed to spend up to certain amount on the two inputs, and then you need to derive labor and capital quantities that will maximize the output. And of course, you have to calculate this maximum output. Okay, and then there are examples on the slides, very detailed, so I don't want to go through the same examples on the slides again. I rather want to look at maybe some of the questions on the study guide. So maybe I would do one questions about minimization of cost. So let's look at this one. This is the isoquant equation, wage, rent, okay. This is the production target, 400, and I want to find out the labor and capital quantity that will minimize total cost in order to be able to produce 400 units. Okay, so we have to derive marginal product of labor, which is dQ over dL, first order partial derivative with respect to L. And similarly, marginal product of capital, which is dQ over dK, okay, with first order derivative of Q with respect to capital. And then marginal product of labor over marginal product of capital, okay, which is the slope of the isoquant. Again, we simplify method, so we take out the negative sign to make it absolute values. And then similarly, the slope of isocost line, it should be minus W over R, but we take out the negative sign, then 1 over 2. And then at equilibrium, this is what happens. Okay. Then you derive this relationship, labor equals 2K, then you substitute into the isoquant equation. Q, you already know it is the production target, 400. And then you substitute the relationship, L equals 2K here. Then you eventually find out this is the capital quantity. And this is the labor quantity. So these are the quantities that will minimize input cost. And then you substitute these two values into the isocost equation. Then at the end, you know that in order to produce 400 units, you have to use 28 something units of capital, more than 56 units of labor to produce 400 units. And this is the minimum cost, 113 Rand. Okay. And then let's do one question on maximization of output. You are given the cost constraint. You are only allowed to spend 396 Rand maximum on the two inputs. Okay, so again, starting off with the same old story, marginal product of labor, marginal product of capital, and then the slope of isocon, the slope of isocost, and then the equilibrium relationship until you get K equals 9L. So let me stop for 30 seconds for you to go through the answers. Okay, and then I substitute the relationship K equals 9L into the isocost equation. We already know this is the cost spending, 396. Okay, then after the substitution and some calculations, we found out that labor is 36, capital is 324. Okay, then we will be able to calculate the maximum output, 66 units. So it means by using 36 units of labor, 324 units of capital, we can achieve the maximum or produce the maximum output of 66 Rand. Okay, under the constraint that we can only spend 396 Rand on the two inputs. Okay, straightforward. Then the last topic is Lagrange multiplier. Okay, this is the other way to solve the constraint optimization type questions. Okay, so this is the story. I want to optimize. Optimize means either minimize or maximize the objective function, which consists of two variables subject to a constraint. Then we derive the new function, which involves x, y, and lambda. You put this target optimization or maximization or minimization target here, followed by plus lambda, then the constraint equation. Okay, and then you derive the three first order derivative with respect to x, y, and lambda. And then these three first order derivatives must all be zero. And then you solve for the unknowns x, y, and lambda. I think the focus will be on x and y. Okay, and this x and y would be the optimal solution. Okay, then we are now going to use the Lagrange multiplier method to solve for the consumption, production, equilibrium type questions. Okay, so let me stop for 30 seconds for you to go through these three equations. Okay, so let's do one question on utility maximization, but now I use the Lagrange multiplier. So I'm going to redo question 7, okay, by using the Lagrange multiplier method. So I want to maximize utility, so I put it here, plus, and then the constraint equation. Okay, what I need to do is just to remember the budget line equation is 1x plus 1y equals 4,000. What I need to do is just to put 1x plus 1y to the other side. Then it becomes 4,000 minus 1x minus 1y. Okay, so this is the whole equation. Remember the constraint equation in bracket next to lambda. Then the first order derivative, dg over dx. See if you can understand how I derive 2x plus 3y minus 1 lambda, okay, equals 0. It must be equal to 0. Then I derive this relationship, lambda equals 2x plus 3y. And then the next first order derivative, dg over dy. Then I have 2y plus 3x minus 1 lambda equals 0. Then I derive this relationship, lambda equals 2y plus 3x. The last one is the easiest, just to let you know, if you differentiate the function g with respect to lambda, you will always get the constraint equation back. Okay, isn't it your budget constraint? 4,000 minus x minus y equals 0. It also means 4,000 equals x plus y. Then you just have to solve by simultaneous equations until you get the relationship x equals y. Then you substitute x equals y into the third equation, and then you get x equals 2000, y equals 2000. So these are the two quantities that would maximize utility. Then the last thing you have to do is just to substitute x equals 2000 and y equals 2000 into the utility equation to get this maximum utility, 20 million. Okay, happy with that? And then let's do one question on minimization of cost. Okay, let's do this one. Okay. We redo question 13, but using the Lagrange Multiplier method. Okay, so the function we want to optimize, which this time is minimize, is to minimize input cost. So this is my input cost, L1L. Remember wage is 1L plus 2K plus lambda. Then you put the constraint equation within brackets. We want to produce 400. Then we move this term to the other side. Then the constraint equation would be 400 minus this whole thing. And then you derive the three first order partial derivative. They must all be 0. So let me stop for 30 seconds for you to go through. Okay, and then equation 1 equals equation 2 because you have one lambda on both sides in both equation 1 and 2. Then you do a bit of simplification until you derive this relationship, L equals 2K. Then you substitute L equals to 2K into your third equation. And then you can solve for L and K. I think these answers are familiar because remember we did this question earlier, question 13, using the conventional method. Okay, then we derive the minimum cost, which is 113 something. Okay, finally, the last one. Let's apply Lagrange multiplier on the second type of production question, which is about maximization of output, subject to the cost constraint. So let's redo question 17. This is a restriction. We can only spend 60 Rand maximum on the two inputs. We want to maximize output. So G as a function of L, K, and lambda. So we rename X as L. We rename Y as K. So this is the function we want to optimize, maximize in this case, the output. Plus lambda, then the cost, then the constraint equation. So I move these terms to the left-hand side. This is why I have 60 minus 5L minus 4K. And then I derive the three first order derivatives. They must all be equal to 0. And again, for the third equation, dg over d lambda, it would give you the constraint equation back. Okay, and then equation 1 equals equation 2 until you derive the relationship k equals 5L over 6, and then you substitute into the third equation. Then you can solve for L and K, and eventually you substitute into the total product equation, then you can find out the maximum production quantity. Okay, so we have covered topic C. So topic C is actually the longest topic for this when it comes to the mass eco part of the bootcamp. And then the last two topics are relatively shorter, matrices and integral calculus. So see you later.